Our next speaker is Rodrigo Perez. He's going to talk about flexibility of entropies in piecewise expanding unimodal maps.
Okay, well, thank you for the organizers for the invitation to speak in this session. This is joint work with Luis Alceda and Michal Miserevich.
Rodrigo, can you show your face?
Sorry?
Can you show your face? Your video is off, I think. Your
Show
video.
my face, yes.
Yeah, so that people can know you, who you are.
All right.
Good.
Hello. So this is just a baby model to illustrate the general program of flexibility that was started by Bocci, Katok, and Rodriguez Hertz. I'm just quoting them. The general idea is that under properly understood general restrictions, within a fixed class of smooth dynamical systems, dynamical invariance can take arbitrary values. And to illustrate that, they mention the following ideas: typical dynamical invariants are Lyapunov exponents or entropies. And if your map is unimodal, then the entropy has to be less than logarithm of 2. That's a restriction that has to be there. If the system is volume preserving, the sum of Lyapunov exponents has to be 0. If it's symplectic, the Lyapunov exponents have to come in plus minus pairs. But other than these restrictions that have to be there, the variation of the invariance is arbitrary. This is the idea of flexibility in a broad sense. And of course, if you do not have complete variability, that always means that you have a general restriction that you have not considered. So it's just a vague notion. And the point of this work is to make a baby, to present a baby situation where this is actually the case. So we're going to work with expanding skew tent maps. And we have two results. One is that if the parameter A is between these two values and the parameter B is less than A, then we can find an expanding mixing skew tent map where the topological entropy is A as required, and the measure entropy is B, where mu is the whole absolutely continuous invariant probability measure of the map F. And a similar result where we just require that the parameter B is less than A, no lower restriction on A. And with those conditions, it is guaranteed that there is an expanding skew-tent map, perhaps not mixing anymore, where the topological entropy again is equal to A and the measure entropy is equal to B. So due to the time constraints, I'm going to spend most of the time explaining what the skew-tent maps are and then give a quick sketch of the proof for theorem A, but not a complete proof. And the proof for theorem B is similar. So skew-tent maps, I'll show the image in just a moment, but these are maps on the interval 0, 1. We are going to choose an arbitrary value for the right-hand slope. Is going to be negative t. And this function goes through the point 1, 0, so the image of 1 is 0. The maximum value is reached for this particular parameter. It only depends on the slope. And that means that the interval c to 1 is orientation reversing, is 1 to 1, and it's expanding because the absolute value of the slope is bigger than 1. It has a fixed point, which again depends only on the parameter t. And there is a preimage of the point C, which will be our critical point, right? And there's a preimage which has a fixed value. Notice that the turn point, the fixed point, and the preimage of the turn point are in this particular order because of these inequalities. They all depend only on the value of t, and that's my map. This is C tilde. I could not put the tilde in the picture for some reason. So that's the preimage of C. C goes to 1, goes to 0, there's a fixed point. And in order to make a skew tent map, what we need is to have another segment on the interval 0 to C. And this segment has to start anywhere between 0 and 1, connect to this point. It's just a linear map. Please notice that slope of 0 will not be allowed. That's not technically a tent map. That's going to be constant on an interval. So we want to avoid that. This is what I just said. And if I'm picking the initial point in this region, then I have slope 1. This is still not expanding. So I need that slope to be larger. If I connect all the way to the bottom, so the 0 is also a fixed point, then I have this slope, and that's the maximal slope that I can have for my tent map. So that I have a range of possible slopes for the left side of my tent map. This inequality is equivalent to the more symmetric one that says that the reciprocal of S plus reciprocal of T has to be larger than 1. This is the linear function that creates that. Nothing really remarkable here. So I have created the following map, which consists of 2 separate segments with those 2 slopes under this condition. And that condition tells me that the corresponding slope S is going to be larger than 1, so my map is expanding. So I have a parameterized version of the space of expanding skew tent maps, parameterized by 2 parameters. And this is my space, right? S and T have to be larger than 1, and the other condition is just a hyperbola condition, so that's my region of parameters. Okay. So there's my formula, there's my tent map, fixed point, turn point, pretty much of the turn point, and the slope is large enough that the slope is larger than 1, but that will depend on the slope of T. I want to point out something that is very confusing when one first starts looking at tent maps. If the slope T is very close to -1, so that the turn point is very close to 0, there's very little variability here, but the slopes can vary wildly. So that the fixed point will be close to 1/2, but changing the slope so that we pass the fixed point will require a very specific kind of parameter. I'll mention that in a moment, but I wanted to show it with a picture. So to recap, those are the values that describe the behavior of the tent map, and those are their images. And oh yeah, and one more comment. For the tent map to be mixing, we are going to need that the image of 0 is lower than the fixed point. Let me illustrate that. Here's a tent map that is not expanding because this slope is less than 1. However, the slope is 1/T, and since this slope is -T, that's a 90-degree angle. So it's a weird, nice tent map. And this particular situation, fixing T and then using that to fix the value of S, we have a curious situation. C goes to 1, which goes to 0, and 0 goes to C tilde, which goes to C. And that means that the interval 0 to C has to map to the interval C tilde to 1, and the interval C tilde to 1 maps back to the interval 0 to C with an orientation reversal. And that means that every single point in this interval has period 4 because of the orientation reversal, except of course the point in the center, which is going to have period 2. And because this slope is always larger than 1, any point between C and C tilde will eventually spiral out and get into the game. So this map is very clearly not expanding. Not mixing. What we're missing here is the fact that the image of 0 completely misses the fixed point, so that this interval lies on one side of the map. So I use this one just as an illustration. For the map to be mixing, we're going to require that the image of 0 is smaller than P. So let's consider one more sample tent map where S is equal to this particular parameter. In that case, the image of 0 is exactly P. And for any slope lower than that, the image of 0 will be lower than P, and then our map will automatically be mixing. And all of this just to illustrate the fact that I can give a complete description of the parameter space of expanding mixing tent maps. So mixing condition requires this. Again, one of those places where the formulas may seem confusing. This condition here is exactly what I'm asking, so that the image of 0 lies lower than P. That makes the map mixing, but I'm also requiring that S is larger than 1 for the condition that the map is expanding. Now, this looks like it's smaller than 1, so that condition would be empty. This is larger than 1 when T is less than the golden ratio. So the mixing condition sometimes is empty, but for a small slope very close to very close to the left, the two conditions are different and they will have different spaces. Mixing, expanding is a proper subset of the space of expanding maps. All right, so here's my map. Here are my two spaces. In the space of expanding maps, we have that the entropy is always less than logarithm 2, it's just a tent map. And in this mixing space, we have the entropy is bounded from below by logarithm of 2 over 2. Okay, so we're going to sketch a proof of theorem A. And it is straightforward. We're going to start with a map, a tent map, where the two slopes are the same in absolute value, because then all the computations are easy if we choose the slope to be the exponent of A, and we take the slopes to be the same with different signs, then the topological entropy is clearly just A. There's a theorem of Misurevich and Vicinescu that tells me that there is a short interval of parameters and a function that takes that interval to 1 infinity, so small region to the right of 1. And this function going to infinity when we approach 1, so that if I have a tent map with the entropy, sorry, the topological entropy of the tent map will be A, if and only if the slopes are negative T and this function beta of T. Now, this slope has to increase to infinity as T gets closer and closer to 1, but I can always find such a map with the same entropy. And moreover, all of these different tent maps have the exact same leading invariant. So the idea is to consider the absolutely continuous invariant probability measure of one of such tent maps. And notice that for the original map with the same slopes, the measure entropy is also equal to A, but as the parameter t, as the slope t goes down to 1, beta increases to infinity, the turn point goes to 0, and then we can check that the measure of the interval 0 to c to the turn point goes to 0, not only in Lebesgue, but in the measure mu. And because of that, since the union of those two intervals is a generator partition, the measure entropy will go down to 0, eventually hitting the parameter b that we wanted. Of course, we have to prove continuity of the corresponding maps, and that's part of the computation. So, if my map is mixing, then this function gives me a density for an absolutely continuous invariant measure, bounded from below on the support, and the support is just a union of intervals. If 0 is periodic, then we can track the orbit of 0 to hit C. The derivatives are going to become problematic because we hit the turning point. So we have to be a little bit careful about how we handle the derivatives, taking limits from the left and the right in the standard manner. So the k derivative is going to be the limit as we approach x0 from the correct direction. And we assign a derivative to the turning point according to the fact that the p minus second iteration of f preserves the orientation or reverses it around the turning point C. But once that we define those derivatives, we have a clearly defined needing sequence with left and right itineraries. And in order to define the itineraries, you just have to take the corresponding limits. Okay. So we have a nicely defined needing theory. If my function is mixing, the image of 0 falls below the fixed point P, and then the needing sequence will have this form. Again, this is confusing. I had to explain this in other talks. Here's the idea. 0 maps to a point below P, and then hits at least one sorry. The turning point maps to the right, maps to 0, so that's the R and the L, and then there's a number of right returns before we fall down to the L, and the only point is that this M can be equal to 0. In other words, if the turning point goes to 1, goes to 0, and then the map is very mixing, so the image of 0 is very low, we hit a lot of left images before we fall to the right again. That would be the case when M is 0. But if 0 falls very close to the fixed point, then in one single step, we already fall close to the fixed point and then have to turn around several times before coming back to the L. The case when M is equal to 0 is the one that creates confusion most of the time. But we want to write our needing sequence in this manner because we can split our space into graded sections according to the number of right returns that we have. We use that to prove the following lemma, which is basically the key to the computation. If our 10th map is in the space Xn, then the variation of the absolutely continuous measure is less than this formula, which depends on n, but also depends on the slope. And the proof is simply bound the variation by the absolute values of the inverses of the derivatives, and just keep track of how many times we hit the left side and how many times we hit the right side, which is going to be either this inequality or this inequality, and we know exactly how many of those we have. So the variation is going to be less than this. We have a geometric series, and we have the bound that we wanted. These are not very difficult proofs, but the whole point of the paper is to prove things from first principles. Good. So in order to have to construct the absolutely invariant probability measure, then we had to normalize, which by York is unique. And here's some samples so to illustrate exactly what's going on. As the slope on the left is increasing, the support of the density is always a collection of intervals, but the values of the density are going to get more and more closer together near 1, right, as this slope increases, which is our next result. Given an n and an epsilon, there is a moment after which, for a higher slope, we can bound that density very close near 1, while at the same time having a very small variation. And the proof basically is to notice that the density is bounded by the same sum as before, which is just a quick geometric series. There is a formula. The variation, we established inequality in the previous slide, and as S increases, both of those bounds are going to decrease, so we can eventually bound them together. So the next step is to show that the density of the probability measure is continuous. Basically show that those densities converge to density of F as a sequence of 10th maps converges to the 10th map in the supremum normal. Again, standard proof of concept. We had to take the density of G, split the series that defines it into the first L terms and the tail. And we estimate the difference of the two densities by bounding the tail of F, the tail of G, and the difference between the heads of the two series. Given any epsilon, we will always find constant T and delta, so that if G is close to F, the slopes of G are always bigger than T in absolute value. And if that is the case, then the tail is simply going to be bounded by a geometric series using that T. So just to get a uniform bound. And we can choose that L to make sure that this number is less than epsilon over 3 right here. We can do the same for the other tail, and we can bound this difference simply by noticing that this is going to be smaller than the sum of the differences of those first L iterates. We can always make that smaller than epsilon over 3, so we have that continuity. The last step in the proof is to show that since we already have continuity of the map from tens to the densities of the measures, we can still get continuity when we have the map from the tens to the density of the probability measures, of the normalized measures. That's, again, just a quick inequality. I'm not going to stay long on this one because it requires a different lemma that I realized last night I had not included in the slides. So let me just mention that the last step is to show that this map, getting from the map to the measure entropy, is a continuous map. And this is just a quick observation that the density is bounded by a constant m, so that if I have two 10 maps that are very close, then the logarithm of the derivative is going to be bounded above by a constant bound. This map is continuous. So that we have, again, bound on both of these quantities, and then all we have to do is do a quick application of Rockley's lemma to see that the entropies, which are defined by these integrals, are bounded by the bounds on these two quantities. So again, nothing spectacular, but this proves the first theorem, and the proof of the theorem in the second case just requires keeping track of the lower bound on the entropy. And I think I actually finished 3 minutes early. So this is the presentation. Thank you very much.
Thank you so much. So let's thank the speaker.